So let us begin today with where we left off last time. I had started talking about the fundamental constants of nature, and we listed 3 of them to start with. The first was the speed of light in vacuum, denoted by c, and recall that the physical dimensions of c was that of a speed, Lt inverse, then Planck's quantum mechanical constant, Planck's constant, and this had physical dimensions of m L squared t to the minus 1, energy multiplied by time, and then there was Newton's gravitational constant, which had the dimensions of m inverse L cubed t to the minus 2. The numerical values of these constants in standard international units, this is 3 times 10 to the 8 meters per second, this is of the order of 10 to the minus 34 joule seconds, and this is of the order of 10 to the minus 11 in standard international units. Okay. I mentioned that these were truly fundamental constants in some sense. Of course, you can immediately think of many other constants of varying kinds. For instance, there is the mass of the electron, which is of the order of 10 to the minus 30 kilograms. Similarly, there is the mass of the proton, the mass of the neutron, and so on, and then various masses of nuclei. They are all constants in that sense, constants of nature. And then there is the charge on the electron, 10 to the minus 19 coulombs. And then there are various other kinds of constants one can associate with these quantities and other derived quantities. For instance, you might say, how about the solar constant? How about a constant like the specific heat of a particular material, like water for instance, or how about the refractive index of a liquid or a solid, and so on. They are all constants of nature, but the point is there is a fundamental difference between this sort of constant and this sort of constant and this sort of constant. For instance, you will say refractive index of water, for instance, that too is a constant. Okay. But there is a big difference between this kind of constant, that and that. This kind of constant refers to specific materials, specific objects, specific conditions, such as the amount of radiation received at a distance from the sun equal to the average distance that the earth is from the sun per unit area and per unit time, and so on. That is the solar constant. This will of course change if you go to another planet or some other distance or another star. The refractive index of water depends on the temperature of the water, it depends on the pressure it is under, and other physical conditions. So in that sense it is specific to a particular substance under particular conditions. The mass of the electron and the charge on the electron, on the other hand, are not of that kind at all. The electron has the same mass no matter where it is in the universe. It has the same charge no matter where it is in the universe. So these are truly constants of nature in that sense. However, they again refer to very specific objects, such as the electron in this case, or the proton or the neutron. On the other hand, these are fundamental in a different sense. They describe various properties of the universe itself in some very, very fundamental sense. They are independent of the objects which this universe contains. They are intrinsic constants in the following sense. This c, according to the special relativity theory, puts a fundamental limit on the speed that material objects can have. So this is in fact a limiting velocity in the universe the way it is. This on the other hand tells you what happens when you go to very small objects like atoms or molecules or electrons, individual particles, nuclei, and so on. It is a quantum mechanical constant, and it starts playing a role as soon as quantum mechanics takes over from classical physics, and you need to include the effects of quantum mechanics in whatever you are describing. So it is a fundamental property of the universe, as we believe. This G tells you another fundamental property in this universe, namely masses attract each other according to the first approximation, Newton's law of gravitation. So in that sense, this tells you something about the large scale structure of the universe. And this tells you something about the very small and the very large here, and this puts a fundamental limitation on velocity itself for deep reasons of symmetry. Okay. So in that sense, these constants have a slightly different role to play than these other constants, and that is why I call these truly fundamental constants of nature. Okay. Now having done that, having said that, one can ask now, after all, my basic quantities I talk about are m, l and t. So is it possible that I can construct from these three constants of nature, which we claim are truly fundamental constants, is it possible that we can construct a quantity which has the physical dimensions of a mass or a length or a time? Very conveniently for us we can do that because there are three of these quantities here which are physical dimensions as written here, and from them we can construct quantities which have individual dimensions, mass, length and time. All we have to do is to put these quantities together in such a way that the other two dimensions cancel out and you are left with either an m or an l or a t. For instance, suppose you construct, as I said last time, it is more useful to talk about h cross, which is h over 2 pi . In physics we always talk about h cross because that is the quantity that appears naturally. Then consider the following, we would like to have, for instance, a mass. So I would like to have a quantity of dimensions mass, and this must be equal to some combination of h cross c and g, and it is obvious from here that if you multiply h cross with g, this mass cancels out immediately. So if you write h cross g here out there, then this cancels out and you have L to the power 5 and T to the minus 3. So this quantity has dimensions L to the 5, T to the minus 3, and we want to cancel out both these fellows. So what you do is, for instance, take a C to the power 5 and look at what the dimensions of this quantity are. The physical dimensions of this are m L squared T to the minus 1 times G, which is m inverse L cube T to the minus 2 divided by C to the power 5, and what C to the power 5 does is L to the 5 T to the minus 5. Okay. So this is equal to, the m cancels out here, the L's cancel out completely, this 5 goes up on top and you are left with T squared. Therefore if you took the square root of this quantity, you have a quantity, the square root of this, which is equal to T. So this says that the combination h cross g over c to the power 5 has the physical dimensions of a time and nothing more. All the L's cancel out. So what would you call this time? It is called the Planck time, T Planck. T Planck is equal to square root of h cross g over c to the power 5. So these three fundamental constants give us a natural quantity which has a natural combination which has the physical dimensions of a time, and it is a fundamental time in nature in some sense. It is called the Planck time, denoted by T sub p, and it is h cross g over c to the power 5. Now it is interesting to ask, what is the numerical value of this quantity? Well, if you put in the figures we already have for this was of the order of 10 to the 8 meters per second, this was 10 to the minus 34, and this was 10 to the minus 11. Then you end up with, this is of the order of 10 to the minus 43 seconds. So it is an incredibly small interval, because if you remember what I said the last time, the smallest time interval that we can actually indirectly probe through our experiments is what is called the strong interaction time scale, and it is 10 to the minus 23 seconds. This is 20 orders of magnitude smaller than that. So let us keep this in mind for a moment, that there exists a natural time scale in nature which is of the order of 10 to the minus 43 seconds, inconceivably smaller than any physical process that we are familiar with. Okay. And those of you who have read about the Big Bang, for instance, might have come across this statement that we know what happened to we have a scenario for what happened to the universe after 10 to the minus 43 seconds after the so-called Big Bang, but before that it is unknown. The reason is buried here, it is buried in this. The fact is, and I will come back to this, the very meaning of time is lost. The present understanding of time, that meaning is lost below a time interval smaller than this, and we will come back to this in a minute. Now having found a quantity of dimensions time, how do we find a quantity of dimensions length? Well, there is a velocity here. So if I multiply this time by this velocity, then it is automatic that you are going to get a quantity of dimensions length. So it is immediately obvious that you are going to get square root of h cross g divided by c to the power 5 square root, and then I have to multiply by a c. So that is the same as multiplying by c squared inside the square root, and therefore you get c cubed here, and this is a length. This is called the Planck length. And this is of the order of 10 to the minus 35 meters. Once again, it is inconceivably smaller than any length scale that we are used to. The smallest length scales that you might be used to is, for instance, the radius of a nucleus, the size of a proton, so to speak. This is of the order of 10 to the minus 15 meters, a femtometer. This is 20 orders of magnitude smaller than a femtometer. So it is inconceivably small, and once again it tells you that there exists a quantity of dimensions length, a natural length scale in the universe which is unbelievably small, much smaller than any physical thing that we know about, and it happens at 10 to the minus 35 meters. So in a sense, just like in the case of time, the Planck time, this is the length scale below which our conventional notion of length as a continuous variable breaks down completely. So these are fundamental properties of the universe as we understand it presently, and it is not surprising therefore that these constants emerge naturally from these fundamental constants here. Well, you could ask, what about a mass? Can I create a mass from these? We already have some elementary masses like the mass of the electron, the mass of the proton, and so on. But there is a mass that we can construct, and that has the following dimensions. Once again, we need to play with these in order to create a mass. This time it is clear that h cross and g must appear in the numerator and denominator so that you get an m squared on top. So this quantity ch cross over g has the dimensions of a mass, and it is called the Planck mass, MP. And again, this surprisingly is of the order of 10 to the power minus 8 kilograms. Now that is much, much larger than any of these quantities, although they are in different units. Now 10 to the minus 30 is the mass of an electron. 10 to the minus 8 is the Planck mass. That is 22 orders of magnitude larger. What does this mean? There is no elementary particle with the mass of the Planck's mass, because that is enormous. This is almost a macroscopic mass. Well, there are many analogies you can give for what this mass is like. I mean, many objects would have this mass. For instance, certainly bacteria perhaps, or even the egg of a flea or something like that would have a mass comparable to this, the Planck mass here. So it does not have a significance, unlike these two cases, as some kind of limiting mass or the mass of some physical object or anything like that, but it has the following meaning, which we will not get into right here. If you have a point mass, a single point particle with no dimensions at all, in some sense the Planck mass poses the upper limit to what can happen for a point mass. More than that, it cannot support a mass, and gravitational collapse would occur. So in that sense, this is slightly different from the Planck length and Planck time, where the meaning of length and time themselves get distorted below these scales. The Planck mass is somewhat different, it has a different footing altogether. But the point of this exercise was to show that you can use combinations of the three fundamental constants to create quantities which have natural length, mass, and time units respectively. So that is what this little analysis said. So keep this in mind, but now let us go on to the next part of it, which is to see how we can use dimensional analysis in order to derive useful information about physical problems. It is a very, very important subject, so let me spend a little time on this. We will repeatedly try to come back to dimensional analysis, and as I mentioned in the beginning, it is a very useful tool, for instance, to check the correctness of formulas of various kinds. So when we do things, other formulas and so on, we will always check the dimensional consistency of these equations by making sure that the physical dimension of whatever is on the left hand side of an equation appears exactly on the right hand side as well. And the problem I am going to choose for illustrating the power of dimensional analysis, we will also see where it is going to fail, what its limitations are, is a very simple problem which is familiar to you in many contexts, and that is the motion of a simple pendulum. Now what we have here is a light massless rigid rod of length L and a heavy bob of mass m suspended from it, and it is free to oscillate about this point of suspension here. So that is what a simple pendulum is. And we want to find out what is the time period of oscillation. So this pendulum is assumed to be we started swinging and then it undergoes oscillatory motion of this kind. It oscillates back and forth about the lowest point under the action of gravity in this form. Okay. So for simplicity we are going to assume that all the mass is concentrated here and there is no mass here at all. The moment you put a mass here, it would be like a rod with a finite mass, then it is called not a simple pendulum, it becomes a compound pendulum. That is a little more intricate, but let us analyze first the simple pendulum's motion here. We are supposed to set it oscillating with some amplitude, and let us call this angular amplitude theta, and I will put a knot here to show that it is a constant under the given conditions, namely I start it off at some angle theta and let go, and by the conservation of energy this angle can never increase beyond theta naught, it stays with theta naught. And if I neglect friction and include only gravity, then this oscillation will continue forever, and this is the amplitude of oscillation. Okay. We will come back to the role of this theta naught here, and the question asked is what is the time period? Time period, and let us call it t, and what is this equal to? Okay. Now of course the way to do this problem is to set up Newton's equation of motion for the motion of this bob, and then solve this equation of motion, show that it is periodic motion and compute the time period. Now that is doing the regular dynamics of this bob, but we are trying to do this by dimensional analysis. So we are going to see how close to the exact answer can we get by doing this. Now the force on this bob is due to gravity, and it is a downward force mg out here, and at any instant in its motion there is always the constant force of gravity acting downwards. Okay. There is also a tension in this, it is a rigid rod, so we are not going to be interested in that because the rod does not extend, and this mg is the force which we have to write down when I want to write down the equations of motion. But I do not want to do that. I want to ask what can this possibly depend on? Okay. Now comes a very important point. It is going to depend on a large number of factors in general, and let us start writing all these down and classifying what they look like. Certainly your first guess would be that it depends on the mass m. It should depend on g because that is the force that is causing the motion in the first place. It should perhaps depend on L, the length of this bob. It should perhaps depend on the amplitude theta naught. So this is the angular amplitude. Some given angular amplitude. Certainly I expect physically that if I take this bob and oscillate it with one amplitude and then I oscillate it with a different amplitude, there is no reason why the time period should be the same, and therefore there should be some dependence on theta naught. My first guess would be to say the larger the amplitude, the longer it takes, the time period. So therefore I would say that there is some dependence on theta naught which is to be discovered as yet. What else could this depend on? Well, no reason why it cannot depend on fundamental constants of nature. So perhaps it also depends on the speed of light, it also depends on Planck's constant, it also depends on capital G. Maybe it depends on other things as well. There are other constants of the motion. For instance, I know that in heat and thermodynamics there is this statement that the average kinetic energy of a molecule of gas in this room is 3/2 kT, where k is Boltzmann's constant. So there is a universal constant, Boltzmann's constant, k Boltzmann. This fellow is called Boltzmann's constant. And its numerical value is of the order of 10 to the minus 23 joules per degree Kelvin. So maybe it depends on that. Maybe it depends on the charge of the electron and a whole lot of other constants. Okay. We have no clue at the moment. And now we bring in physical arguments to eliminate things. Well, you could also ask one more thing. You could say, look, after all, when it's moving, the angle is changing. At some instant of time when the bob is here, the angle is theta. This angle is theta. And then it increases up to theta naught, comes back, becomes negative, goes up to minus theta naught, comes back to 0, and so on. So maybe it depends on theta as well. Maybe it depends on the rate at which this theta changes. That too is crucial. So maybe it depends on the angular velocity, omega. This is angular speed, and so on. So it looks like a hopeless proposition, but now comes the physical arguments. We are going to make careful physical arguments to show that it actually does not depend on most of these things. It depends on a very small number of these objects, these quantities, and we will get practically the exact formula by careful physical argument, and that is what. So now let us step back and ask, what is the difference between these quantities and these quantities? Well, these are variables. They are dynamical variables. They change with time. As the pendulum swings, theta changes, the angular velocity changes, and so on. But we are asking for a time period which comprises the full motion from here to there, back through here, back to this point here. And therefore, we are asking for a quantity, the time period, which is not dependent directly on the instantaneous velocity or the instantaneous speed or angular speed or amplitude. So these are dynamical variables. The time period does not depend on these variables. It will depend on them indirectly in some sense, but once you finish computing the entire motion over a full time period, it cannot depend on what the instantaneous velocity is at any particular instant of time during its path. Okay. So it is going to depend on these quantities which are not variables, they are parameters. So that is a crucial difference. These objects are parameters. For a given pendulum of a given length, given mass, and so on, and on the surface of this earth where this is given, these quantities are not variables anymore. Even the amplitude is not a variable for a given state of motion. If you tell me how much you pulled it to the left and let go, the amplitude is fixed once more. So the amplitude, the time period could possibly depend on any of these. But now let us eliminate these quantities. I mentioned that this C plays a role as soon as you have either very high speeds or something like light involved, electromagnetic radiation involved, electricity and magnetism involved. This is a classical mechanical problem. This object is neutral, there are no electric or magnetic forces, so we do not expect it to depend on this. This is a big object relative to an electron or an atom or something like that. So no quantum mechanics or quantum corrections come in here, so it does not depend on this. Okay. The object is electrically neutral, so there is no dependence on that. It is at fixed temperature. We are not talking about the transfer of heat energy from one object to another or anything like that, so it does not depend on that. Okay. It does indeed depend on G. But the point is that dependence on G is buried here in little g. Now what is this little g equal to? Remember that on the surface of this earth of radius capital R, if you put a little mass here m and the mass of this earth is capital M, then the force of gravity on this object is by Newton's law g m m divided by r squared. That is the force of gravity on the surface of this earth at a distance capital R from the center of the earth, and we are saying that this is equal to m times g. By definition of little g, this m cancels out. So you see little g is capital G m over capital R squared, where capital R is the radius of the earth and capital M is the mass of the earth. So that is already in this constant here. So we do not need to put this in separately. That leaves us with just these 4 quantities on which the time period could possibly depend. So you see the physical arguments that have gone in here to eliminate all the other variables, and we are going to use that in other less trivial instances as well. So where does that get us? It tells us that this time period must be proportional to, so in terms of dimensions, the dimensions of this are time itself, this must be equal to the quantity m, which has dimensions of mass, raised possibly to some power a, could be 1, 2, minus 1, we do not care, we do not know. It could depend on L, and that raised possibly to some b. Then little g raised possibly to some power c, which we do not know as yet. And then theta naught, but you see what is theta naught? It is the angular amplitude. But as you know, the physical dimensions of angle angle is dimensionless, because an angle is defined as the arc divided by the radius here, and an angle is dimensionless. How do you find the angle between 2 lines? What you do is to draw an arc of a circle and argue that the arc divided by the radius is equal to the angle between the two. Since the arc and the radius both have dimensions length, the angle has no dimension at all. So this is dimensionless. And by the way, we measure always in physics angles in radian measure, not in degrees at all. But it is now a dimensionless quantity, and it could depend here, it could appear anywhere here in this formula. So the time period could be some arbitrary function of this amplitude theta naught, some function of the angular amplitude. And we do not know what this function is, nor have we any way of finding out what this function is. That is the interesting thing, but it is sitting there, and now what we can do is to say, all right, so this will tell us that t must be equal to an m to the power a from this, and L to the b from that, and g was Lt to the minus 2, so L to the c t to the minus 2c from this, and this should be equal to t, which will of course immediately imply that a must be equal to 0, minus 2c must be equal to half or equal to 1, or c equal to minus a half, and that tells you what c here is. So, sorry, this is b plus c, so L was b plus c, that is right, and b plus c must be equal to 0, which says b equal to plus a half. Okay. So if you solve these 3 equations and write it down, we have our formula here for the time period of a simple pendulum, which says that the time period must be equal to some unknown function of the angular amplitude multiplied by m to the power 0, so the mass does not appear at all. L appears of course, and t appears here, g appears, so square root of L divided by g, because c was minus a half while b was plus a half, so it is just a square root of L over g. So that is our formula for the time period of a simple pendulum in this case. It depends on the square root of this length, and it depends on 1 over the square root of the acceleration due to gravity here, but it is multiplied by this unknown function of the angular amplitude, and we have no way of finding out what this function is from pure dimensional analysis because it is dimensionless. Okay. On the other hand, we can say a little bit about it, which I will, and you will see how we can proceed from this, but the fact is that no matter what this function is, and this is the crucial point, the consistency of physical dimensionalities on both sides of this equation says that given a simple pendulum of length L and mass m and gravity little g, given the acceleration due to gravity, the time period has to be proportional to the square root of L over g multiplied by some number which is possibly a function of the angular amplitude. Okay. Now the next time we will see what we can say about this number.